how to balance a redox equation. So sometimes you watch conversations go really poorly, and so like I apologize for this. This is how it makes sense to me, and so I'm going to share this with you. But if you don't like it, just memorize how to do it. So oxidation number is a bookkeeping scheme. So it's totally pretend in a lot of cases. And it's the same kind of idea as formal charge that we talked about a really long time ago. So I'm going to talk about formal charge for a minute. It's not really related to what we're talking about. I'm just trying to show you like they are two limiting behaviors of what might or might not be true. So the spirit of this is the same, but it's going to be like a different limit. So flashback to formal charge. So this is going to be in chapter 14. And you might remember in chapter 14, I would have asked you to draw a Lewis structure for an ion like cyanate ion. Now cyanate, is a linear triatomic, which means it's written in an order that's not really easy for you to guess, but the carbon's in the center. So I underline it for my freshmen and admit that it's not really part of IB, so I underline it for you. So it's obvious to me that it's central, but it's not totally obvious. We write it funny. So I want to think about how I would draw that Lewis structure. And so to draw a Lewis structure, I typically try to count up the valence electrons. I get 16. I put that central carbon in the middle. I draw single or sigma bonds to the two things it's attached to. I say that's 4 of the 16 electrons. So let me fill in the octets on the terminal atoms. I say, uh-oh, I've now used all 16 electrons, but the central carbon does not have its octet satisfied. So I need to promote some lone pairs into multiple or pi bonds. And so I have choices. I can promote 2 from this side, 2 from this side, or 1 from each side. And so I can draw those structures. And it'll take me a minute to make them perfect. But these are the structures I have in mind. That was particularly ugly. But those are the structures. And I believe that if you count carefully, you'll see that each of them have 16 electrons. Each of them have the octet satisfied on all of the atoms. But you might have some opinions about which one looks the least stupid. So there's like more rules than just octet rule in discriminating between Lewis structures. And the rule we typically use is formal charge. Formal charge has like a definition. The formal charge can be calculated by counting the number of valence electrons. That is the number of electrons it should have based on the periodic table, and subtracting the number of bonds and the number of lone pair electrons. If you don't like the formula, which some of you undoubtedly won't prefer, the way I'm sure I tried to convince you to do this was to say formal charge is the limit where all bonds are perfectly covalent. So I'm going to ignore that there's a difference in electronegativity between carbon and oxygen, and what I'm going to say is that the 6 electrons that are in that triple bond are going to be split evenly between the oxygen and the carbon. So when I look at this oxygen, based on the periodic table, it should have 6, but this guy has 1, 2, 3, 4, 5. He's short 1 electron, his formal charge is +1. Carbon's going to split that single bond. Carbon should have 4, it's in group 14, and it has 4 that it kind of owns in this picture because we're assuming perfect sharing. And then nitrogen should have 5 based on the periodic table, but in this picture, 1, 2, 3, 4, 5, 6, 7. Seem familiar? The sum of the formal charges is always equal to the overall charge on the molecule. And most of you would look at that and say that looks awful. Now DT would have stopped looking at this structure early on, because she's saying to herself, I want a structure that looks good. And to me what looks good is that oxygen always makes 2 bonds. And here I'm asking it to make 3. Like I know what water looks like. Oxygen makes 2 bonds. That's how oxygen plays. And nitrogen, it makes 3 bonds. It makes ammonia. It does not make 1 bond. Like, neither of these atoms are doing what they're supposed to do. And so I can use my chemical intuition, if you like, to say that this is terrible. But Sophia is going to use her formal charge and say that the magnitudes of the formal charges are big. There's too much charge here. So we can do this mathematically, or we can do this like just, that looks crappy. Both acceptable.
When you were drawing the structure, is it fine if you put it in brackets so that the negative comes?
But when we look at these two, it's less obvious which is right. Because here oxygen is happy with its 2 bonds, nitrogen is sad. Here nitrogen is happy with its 3 bonds and oxygen is sad. And so again, if you have some intuition, you might be able to decide which of these is better. But if we can't immediately discriminate, we're going to go back here and assign formal charges. And I'll just pretend I'm pretty good at this because I did do it yesterday. And what you're going to find is that the nitrogen in one case has the -1, the oxygen in the other case has a -1. In both cases, the thing with formal charge, the thing that doesn't have the right number of bonds or doesn't have its valency figured out the way you think it should. And we argue that this structure is the winner because oxygen is more electronegative than nitrogen, and so slightly better at stabilizing that negative charge. Like sometimes I can just see that people remember this. So, is this real? No. Like, it's not true that there is perfect sharing. It's not true that these 4 electrons are split exactly 2 here and 2 there. It's just the limit that I use to try to decide that this is the structure that I think is most likely. Quinn's going to go into a lab and he's going to try to figure out something about the stretching frequency of this bond. Does it correspond to a CN triple bond or to a CN double bond? Could we find support that this is the best structure? What I think he's going to find in terms of bond length or vibrational frequency is that it's somewhere intermediate between these two, probably a little bit closer to this one. So we have like a model. It's based on a pretty easy limit, but it's not real.
Could you explain why the middle one isn't favorable because you mentioned oxygen?
So the reason that we use formal charge is that to say that we're going to put negative formal charge on the most electronegative atom. So we have a choice here, right? We can put that -1 formal charge on either the nitrogen or the oxygen, and we're going to choose to put it on the oxygen because it's more electronegative. So rule number 1 is minimize it. That's why we threw this one out right away. It just looked bad to us. But here it was not as obvious which one looked bad. So we tried to apply this second rule.
So if we went to a lab and we looked at the different structures like Quinn was going to do,
Yeah.
would it be more probable that we find a triple N bond? Is that kind of what happens? That it's more probable that we find a triple N bond, but it is also likely that we could find.
So we're going to find some sort of an average between the two. Yes.
Okay.
And so the average, I think, is going to tilt closer to the triple bond in terms of length or strength. So oxidation number is the same kind of thing. It's a little bit pretend, but it's going to be the opposite extreme. So formal charge assumed perfect sharing, that all bonds were perfectly covalent such that each guy got one of the electrons. We are now going to assume absolutely no sharing. The more electronegative atom is going to steal the electrons. So I'm going to call this the ionic limit. Yes. The ionic limit is what I'm going to use for oxidation number. The covalent limit is what we just used for formal charge. And so I was thinking about Audrey's, are we all thinking about it? So what Audrey was doing was, I didn't think about Audrey's IA for last class, until later in the conversation. Okay, in a not balanced, but at least reasonable looking formula, what I have on the left side is ethanol. And I'm gonna take ethanol in the presence of acidified potassium permanganate or acidified potassium dichromate. And usually we use a little bit of heat. And we know that those are the conditions that would allow us to make a carboxylic acid. In chapter 10, we learned that we could take a primary alcohol and turn it into a carboxylic acid by using either the potassium dichromate or the potassium permanganate. Remember that? Yeah. And so I know this is supposed to be oxidation, but I don't see oxidation. I don't know if you see it. But I don't have a way of proving to you that anything is being oxidized or even a clear idea what oxidation means based on this. There's no oxygen. So maybe if I went back in time, you ever want to cry when you see other people writing on the board? This is the third unit for Chem Honors. She's starting with it. Why can't we ever be on the same page? So another experiment that I think you guys are super familiar with is more of a chemical reaction than an experiment, I guess. Is that one? That should look like cellular respiration, I hope. Oh, that looks very tired. Look how pathetic he is today. I think he's gonna fall asleep, so someone's gonna have to jab him. So sad. I feel like I missed you more than you missed me. Hello. So this is cellular respiration, and because oxygen is one of the ingredients, I feel like I could say, even if I can't prove it yet, that something was oxidized. Do you agree that I could say that the sugar is being oxidized?
Yes.
Because the oxygen is doing something to it. But I want to figure out, what does that mean? What does it mean to oxidize something? And so I'm going to give you a definition. Oxidation in the modern era does not mean add oxygen. It means lose electrons. So my silly little acronym here, oil rig, oxidation is loss, reduction is gain. Helps me remember that, but I need to count how many electrons it has if I want to prove to you it lost some. So let's try that with Audrey and her alcohol. I'm going to draw you a Lewis structure of alcohol. And you're going to have to tell me what's more electronegative than what. How does oxygen compare to hydrogen? How does oxygen compare to carbon? And so what I've done is I've bracketed in those bonds because oxygen won those battles. So how many electrons does oxygen have in this picture? Total. 8. And it should have 6. And so oxygen right now has an oxidation number, of -2. How about hydrogen? How many should it have?
1.
Should have 1. It comes to the party with 1 valence electron. And because it lost this fight, how many does it have? So it's +1 in terms of its oxidation state. So this is not its formal charge, but it's the same kind of idea. I'm counting how many electrons it has based on it losing both of the bonding electrons to oxygen.
So hydrogen is +1 because it lost 1 electron, but oxygen is -2 because it gained 2.
So I'm just going to keep doing this. Hydrogen is less electronegative than carbon, so I made carbon win those. But carbon is exactly as electronegative as carbon. So there is no winning and losing there, so I'm gonna count up. All of the hydrogens are gonna be +1. This carbon is gonna be, it's got 2, 4, 6, 7. This carbon has 2, 4, 5. Oh, the carbons are different. Crazy. Crazy.
1, 2, 3, 4, 5, 6. Yay!
What is the average oxidation number of carbon in ethanol?
Average, like average, like.
I'm gonna do the same thing for vinegar. Carbon beats hydrogen, carbon ties with carbon, carbon loses to oxygen, hydrogen loses to oxygen. Hydrogen's gonna be +1. Oxygen's gonna be -2. This carbon here is gonna, it only has 1 electron, seems to be +3. This carbon here, has 7, it's gonna be -3. What's the average?
Of the carbons?
And so if carbon went from, on average, having 2 extra electrons to having 0 extra electrons, what happens to the carbon? It got oxidized, it lost electrons. 4 electrons were actually lost in this process. Now you can see it's this carbon that's changing. Like officially I can point to this carbon and say it went from -1 to +3, it's lost 4 electrons. But do you not admit that this was kind of a lot of work? And if I were to do it for this, I'd have to draw glucose, which I have to start practicing because I hear biochem's coming up soon. But then I would have to start, like, things would get complicated. I don't want to have to draw the Lewis structure for everything. So I'm looking for a way to simplify this, which is coming next. Not always having to draw the Lewis structure. But I'm going to answer a question before I do that.
How about with like the oxidation number for like the second one?
For this one,
Yeah.
so carbon should have 4 electrons. But in this picture, it only has this 1 electron because it split it with the other carbon.
Oh, and
It's lost to both sets of oxygen. So I find this interesting, perhaps too much, but I also find it like burdensome. I cannot picture that every time they ask me for an oxidation state, they're expecting me to draw a Lewis structure and figure out the electronegativities and then do a bunch of math. I don't think that's the intent. What do you notice about hydrogen in both of those pictures? What is it always? How about oxygen? And so there's actually a list of rules that we can make based on electronegativity values without even like drawing the picture. And so I'm going to try to write down those rules. The first rule is going to be that the sum of the oxidation numbers, just like the sum of the formal charges, has to add to the overall charge. These rules are supposed to be written in order of importance. So my number 1 rule is that one. My number 2 rule is going to be that an atom in an element has an oxidation number of 0. What I'm trying to say, and think I have said very poorly, is that if Audrey says, what is the oxidation number of iron in like a block of iron, I'm going to say, oh, that's an atom of iron in the element iron. It is 0. What is the oxidation number of oxygen atoms in the molecule oxygen? It's 0. How about in ozone? That's an allotrope of oxygen. O3, it's 0. So anything that is made up only of one atom. How about C60? Diamond, graphite, graphene, buckyballs. 0. So that's what this rule means, even if I've said it in a non-perfect way. The first thing I'm going to do is I'm going to take the least electronegative things I have in the periodic table. And those are going to be the metals in group 1, group 2, and group 3. And they are going to have oxidation numbers of +1, +2, and +3. What do you think I'm excluding by saying group 1 metals? That's right. And again, this is supposed to be a seriatim, or a ranked list of importance. So it's not that hydrogen's not likely to be 1, it's that I can think of some examples where it's not. And so the rule that will supersede that is going to be that the group 1 metals are +1. Fluorine is the most electronegative atom we've got, followed by oxygen. I'll get it right someday. Followed by oxygen, followed by the group 17s, I guess, in order, the group 16s, the group 15s. At some point, you get to pray. Like, you don't know. Like, I can make up arbitrary rules, but if I need more rules than that, I'm done. So the technique that we're going to use is we're going to look at a molecule or anything. We're going to look at a chemical species. We are going to assign all but one of the elements in it an oxidation number based on this, and we're going to take that last one, and we're going to be like, let's figure out what it is. You'll see there is no rule for carbon because carbon's super variable. Yes?
I have a question. You drew ethanoic acid over there, but they were talking about
I drew ethanoic acid over there, but
the equation is just one equation. So
I was just drawing the ethanoic acid that Audrey was making over there because I felt like I didn't have the room. So let's think of some easy examples. What if we had sodium chloride? What's the charge on sodium? What's the oxidation number of sodium?
I'm sorry.
The charge on sodium is officially 1 plus. The oxidation number of sodium is +1. That stupidity is worth a mark each and every year. Order of the plus sign. Charge on chlorine, 1 minus. Oxidation number of chlorine, -1. In ionic species, the charge is the oxidation number. Like, there's not a lot of magic here. It's not surprising, you already knew the answer. How about in water?
the charge on the oxygen.
Both. I want to know the oxidation number of both. So there's no charge, right?
Oxidation number for hydrogen is
Yep. And I'm going to pretend I don't know oxygen for a second. And I'm going to use a formula that's the most, like, complicated way I can imagine doing this. But I'm going to say hydrogen's rule is more important. I don't know oxygen. You're guessing it's -2. I'm guessing it's -2. And look, it's -2. But at least I did it algebraically and got it. But the reason that the hydrogen rule has to beat the oxygen rule is because anyone who's ever bleached their hair apparently knows about that compound. I was reading about bleach because Mohab and I are talking about bleach and his IAL, and I agree with
CL, it would be 1 minus and then minus.
Yes. So that is hydrogen peroxide. Hey, we don't call it oxide. She's wearing earphones. You are wearing earphones, comma, what a punk. Feel free to explain to her what's going on, anyone who's kinder than me. I guess I'm over here. My boss is already gone. It's over.
You know, like they're not on.
It don't matter. It's okay, leave them on. Like, my boss is gone. So everyone who's doing this in their heads is saying, oh, we actually call it peroxide because the charge is different. When oxygen has an oxidation number of -2, we call it oxide. When 2 oxygens each have an oxidation number of -1, we call it peroxide. Another one that's kind of fun is, you might recall that you could take the vinegar that Audrey so carefully made, and you could react it in the presence of lithium aluminum hydride. What would you make? Yeah, we're gonna go backwards and recreate her alcohol. But lithium aluminum hydride is an unusual looking compound, isn't it? Hydrogen's at the end. We don't usually put hydrogen at the end, we usually put it at the beginning. It's not very electronegative, and we call it hydride. Ooh, maybe there's something to that. So why don't we try to figure out the oxidation number of each of the things in lithium aluminum hydride? What's lithium? +1. What's aluminum? +3. So what's hydrogen?
If lithium is 1, is the charge?
Charge is 0.
The overall charge is 0.
Oh my goodness.
Hydrogen, you bitch.
So that's why the hydrogen rule is after the lithium rule, after the aluminum rule, because it's doing something you wouldn't expect. Hydrogen is more electronegative than lithium and aluminum. Hydrogen wins in this weird case. That's why we call it a hydride. Hydride means that hydrogen has a -1 charge.
So what's the X?
What's the X?
Yeah.
Hydrogen. So I make X the last thing I get to. So the first rule I get to here is group 1 metals. Lithium is +1. The next thing I get to is aluminum is +3. Now I've accounted for 2 of the 3 atoms in my thing, so I've got to quit and go back to the sum has to be 0. And so I'm going to take 1 for the lithium, 3 for the aluminum, and all of the hydrogens have to add up to 0. And so that's what I tried to write here. 1 for the lithium, 3 for the aluminum, and all of the hydrogens have to add up to 0. So the hydrogens have to be -1.
Okay.
So I'm always going to leave the last one as my unknown.
0 is the total.
0 is the total because it's a neutral molecule. So let's go back to the alcohol. You see how I carefully didn't erase this, even though it would have been very convenient. And let's say, what if we had not drawn the Lewis structure and we had just tried to apply these rules? The first rule I'm going to get to is hydrogen is 1. The second rule I'm going to get to is oxygen is -2. I don't have a rule for carbon because it does what it wants. But I'm going to take 6 minus 2 is 4, plus 2x is 0, x is -2. Oh my god. You got it right. So we don't have to draw that Lewis structure, we can just apply this list of rules. Now the downside is you have to memorize a list of rules, the upside is you don't have to draw a Lewis structure. The rules aren't surprising, but the order of them is a little bit weird. Relatively sure I got it wrong yesterday. At least they don't record it, right? Oh, I think you miswrote that. Let's see how we did with the ethanol. The ethanoic acid, excuse me. 2x, I still don't know what carbon is. 4 1s for the hydrogen. 2 minus 2s for the oxygen is equal to 0. What's x, everybody? Oh my gosh, we got it right. And so we can see like more quickly that on average it's gone from -2 to 0, or on average it has lost electrons. So that's how we do it. To decide what's being oxidized and what's being reduced, you're simply going to calculate the oxidation number. You calculate the oxidation number by trying to employ those rules. It seems like there are a lot of them, but frankly, it's not that unusual.
No, it's just like not, she's still here.
Yeah, like, how do we know what that makes sense?
If you're looking for, it's just like if you're
For this one,
no, she's asking next.
Like, but like, how do we know which one's X for?
The last, so you take how many, let's do this. I feel like I'm gonna need it in a minute. So how many different types of atoms are there? 3. So I'm gonna look here for rules for the first 2. So what's the first rule I get to?
Oh, okay.
So that's how I decide. It's always the last one that may or may not have a rule that I'm gonna keep as X. So what is X in this case for potassium permanganate? I told you that the product was this. What's the oxidation state on manganese 2?
0. Oh.
So it's just what is there.
Because the sum of the oxidation numbers has to equal the overall charge.
Gotcha.
So does that look like reduction?
Yes.
Yes, wait. Reduction is.
Gain of electrons.
Yeah.
It does, because we gain 5 electrons. So now I have this, from the top one, which was +7, so missing 7, to the bottom one, which was +2, so missing 2, he got 5. So, let's,
Is the reason why we set it equal to 0 because the atom
in number
number 2?
2, yeah, all of them are neutral things. So if you just have like O2, it's neutral, yes.
Quick question.
Yes?
So, like a number where it has the coefficient, you don't like factor that into the oxidation number, right?
What?
Like for example, in ethanol with the H5, wouldn't like do 5 times the 1, right? It's just the,
5 times 1?
you do that.
Oh, sorry, the oxidation number of hydrogen is +1,
No matter like the coefficient.
no matter the number of hydrogens, yes. Sorry, excellent question. So let's check this out. Trying to remember IAS, it's not that creepy of a thing. That's a single replacement reaction. Chlorine is a more active nonmetal than bromine, so chlorine's going to become part of that compound. What is the oxidation state of chlorine in chlorine? What is the oxidation state of bromine in sodium bromide? Chloride is going to look the same, bromine is going to look the same. Is that reasonable? I'm just doing the halogens for a minute. So what's happening to chlorine here? How many total electrons are being gained? How about here? And how are you getting that it's 2? because of the coefficient, because there are 2 chlorine atoms, each of which is gaining 1 electron, because there are 2 bromide atoms, each of which is losing 1 electron. What do you notice about the number of electrons gained and lost? It's the same. It will always be the same. It is in fact a rule. When we balance a chemical equation, you know that we have to balance it so that there are 2 chlorines on both sides, 2 bromines on both sides, 2 sodiums on one side, on each side. But sometimes I think you might forget that you have to consider charge. So I'm gonna think about taking, this is Brecken's experiment, but he's not here to defend himself. So he took zinc and mixed it with copper and made copper and zinc. What's being oxidized?
Copper.
The zinc is being oxidized, the zinc is losing electrons, the zinc is going from 0 to +2. What is doing that? What is oxidizing it? That's right, we actually call copper 2 the oxidizing agent. What actually happens to the oxidizing agent, if I may ask? It's reduced. That's curious, isn't it? What's a travel agent?
One
Huh?
that facilitates the travel.
That's right, they don't travel like you do. What's an oxidizing agent? It's something that's going to oxidize you. It is not the thing that itself gets oxidized. So an oxidizing agent is the thing that is going to be reduced. Because it's got to oxidize someone else. But I was thinking about redoing Brecken's experiment, changing the oxidizing agent, because he's not here. Let's make it this. That says AG. Looks very artistic, but it means silver. Does that look good? Bad? It's pretty. I wrote well, but Audrey's saying it's a no. That's a tough one.
Oh, because it's not the amount of oxidation.
That's right. Here I'm taking zinc and it's losing 2 electrons, but the silver's only taking 1. Or the total charge on the left side is +1, the total charge on the right side is +2. That's right out. To balance this equation, I need to make sure that the number of electrons that are oxidized is equal to the number of electrons that are reduced. So the electrons that are transferred are always equal. In a balanced chemical expression, are there ever free electrons? Have you ever seen electrons written in an expression? So don't put them there. You've done it wrong. Unfortunately, balancing these things can get hard. And so let me show you how to do it when it's exciting, like when Audrey is oxidizing ethanol. So you might recall that what she did was she took permanganate and she added it to ethanol, and she made manganese 2 and ethanoic acid. Now I know she thinks she used potassium permanganate, but I find that the potassium is just one more confuser. The potassium is a spectator ion, it doesn't do anything, it just makes your life more complicated. I'm gonna ignore it for now. We can put it back in if it makes her happy. Is this equation balanced? No, not even remotely, right? But I also don't know how to balance it. It's not something I can balance by inspection for at least 2 reasons. 1, I'm not very good at it, and it looks complicated. And 2, like, I'm kind of lying to you. Because I haven't shown you that there are other ingredients here. I know that the conditions are heat, which I won't show, but it's acidified potassium permanganate. And the fact that it's acidified potassium permanganate means that this solution is occurring in an aqueous solution in the presence of lots of H+. In fact, if there's not enough H+, she gets this weird brown stuff because she doesn't oxidize it completely. see if we have time for that. We might have time for that tomorrow. So the reason that I think this is so hard to balance is because there's other ingredients that don't even show, because they're not there they're there intentionally to make the experiment work. But when I think about making sure that I am reducing something and oxidizing something, I don't always think about how to balance it. What is the oxidizing agent here? To say something that's important to me, but not apparently to the IB, I've never seen this worth a mark. What I've learned is that manganese is being reduced, and permanganate is the oxidizing agent. So an atom is being oxidized or reduced, but the agent that's doing it is the actual chemical. But I think that's like a hang-up I have and not real. But I'm like kind of strangely emotional about it. So in order to balance this, what I'm going to do is I'm going to break it into two half reactions. A half reaction shows only one of these processes at a time. It's going to show either the reduction or the oxidation. What's cool about a half reaction, if anything is cool about it, is that electrons actually show up. Because if you're showing me reduction, I need to show the gain of electrons. And if you're showing me oxidation, I need to show their loss. So these will show the electrons explicitly. The reduction reaction is based on this framework of MnO4 minus becoming Mn2 plus. It's going to take me a minute to write it, so I'm just not going to pretend I can win it that fast. Not balanced. To balance it, I'm going to go through a few steps. I'm going to write the steps over here and perform them there. So step one, I'm going to balance everything but the O and the H. In this sentence, that's just manganese. How am I doing?
That's fine.
Is the manganese balanced? Do I have one manganese on both sides? Done. Two, I'm going to assign oxidation numbers and add electrons. Oxidation state of manganese here is +2. Oxidation state of manganese here is +7. So I've got to put electrons in. Going from +7 to +2, that's 5 electrons. They're being gained. That's another way of saying that they are reactants. Step 3. I'm going to balance the oxygen atoms by adding water. Remember, this is taking place in an aqueous solution, so if I needed a little water, it's there. And if I made a little bit of water, who could tell? Like it's swimming around in a beaker full of water. And so I'm going to look here, and I'm going to say that there are 4 oxygens on the left side. Well, we best make sure that there are 4 oxygens on the right side. I'm going to skip a step. I'm going to balance the hydrogens by adding H+. How many H's are on the left side? How many are on the right side? So 0 and 8, so I'm going to add 8 H pluses. Check. I'm going to count up the total charge on the left-hand side. I have 8 pluses, a minus, and 5 more minuses. The net charge on the left-hand side is what? The net charge on the right-hand side is also 2 plus. Rock star. We did it. That is a balanced chemical expression. If you watch Khan Academy, I see that in some futures. They won't do this step. They'll just add the electrons here. They'll just fix the charge of the electrons. I do this step to check my work because I know I make mistakes. So I do one more thing that I absolutely have to do because I know I'm prone to errors in this. I try to make it idiot-proof because I make mistakes, as you all know. Let's try another one. We're gonna take ethanol and turn it into ethanoic acid. Is everything but the oxygen and hydrogen balanced? The 2 carbons on the left, there are 2 carbons on the right.
Yeah.
Done. Let's assign some oxidation states. Thank God we did this earlier. This is +6 and -2, so that's +4. So this carbon was -2 on average. This is +4 and -4. This carbon is 0 on average. If carbon is going from -2 to 0, how many electrons is carbon losing? How many carbons are losing 2 electrons? So how many total electrons are being lost? Excellent, 4. Oxidation will always have electrons being lost, electrons being given away. They'll always appear on the product side. We're going to balance the oxygens by adding water. On the left-hand side, I have 1 oxygen and ethanol. On the right-hand side, I have 2 oxygens and ethanoic acid. Need to add water. Now I need to balance the hydrogens. On the left-hand side, I have 8. On the right-hand side, I have 4. I need 4 more. The right-hand side, I add them as H pluses. Now I check for charge. The left side is neutral. The right side, neutral. Rock star. No, it's not. This is like your Euler's method thing. This is scripted. There's one more step. We'll call it step 6. We have to combine these 2 things. How many electrons are being gained in that first step? In the reduction. 5. How many electrons are being lost in the oxidation? 4. We know that the total number of electrons that are lost has to be equal to the total number of electrons that are gained. In a redox process, those 2 problems are always equal, so we need to find what the mathematician in the room will lovingly call the lowest common multiple.
Yay.
What's the lowest common multiple of 4 and 5? 20. So I'm going to multiply this top equation by 4. I'm going to multiply this bottom equation by 5. Now I'm going to add these 2 glorious equations together to get the overall balanced chemical equation that was going on in Audrey's flask.
32 plus.
Woo! She's got 32 H pluses plus 4 permanganates plus 20 electrons plus 5 waters plus 5 ethanols, making 4 manganese 2s, 16 waters, 5 ethanoics, 20 electrons, and 20 H pluses. Audrey's like, that seems a little wordy. I think I could simplify it by canceling things that are on both sides. If there are 20 electrons on both sides, just like in algebra, we delete that. Okay, that's gone. I also notice H plus appears on both sides. I have 32 on one side and 20 on the other, so I'm going to make that 32 into a 12. And water. I've got 5 waters on this side, 16 waters on that side. Make that an 11. That's it. That is the balanced chemical reaction of potassium permanganate. Oh, she's nodding like I did it right. Of potassium permanganate reacting with ethanol to make ethanoic acid and manganese 2. It's pretty groovy, right? Now you have time to practice this on the homework. If this is the skill you want to practice, you want to turn that homework sheet over and do the last 2 problems. If you want to practice just deciding oxidation states and stuff, you can start on the first page. If you go to Khan Academy, they will also balance in base. We do not have to balance in base in IB chemistry. It is no harder or easier than this. It is just one more thing you don't need to do. All of your things will be in aqueous acidic solutions. One more comment and then I'll really shut up. What you'll find is in, I think it's table 24, I'm not totally sure, that there are a few of these already balanced for you. They're there for reasons that we'll talk about in like 2 or 3 days, but they are in the data booklet, so you'll see those in the next class or 2. And so traditionally in a problem, that Mohab is looking forward to. They're gonna make Mohab balance 1. Mohab's gonna copy the other one from the data booklet, because he's gonna know where to find it, and then he might have to combine the two. So traditionally, they ask you to do this one time on an exam, and like, you're gonna practice it 3 or 4 times, and you're gonna be like, it seemed hard, but I can do it. You can do this. Okay, now you can work. Yes. Yes.
So I knew that the manganese was going from +7 to +2, which meant the manganese was gaining 5 electrons, so I added 5 electrons